Hello again. In this video, we're going to talk about invertible linear transformations. By definition, a linear transformation t from Rn to Rn is invertible if there exists a function s also from Rn to Rn such that the composition function s of t of x is equal to x and the composition function t of s of x is also equal to x for all x in Rn. We call S the inverse of t, and we denote it as t raised to the negative 1. Sometimes we use this notation for composition functions, and then it's just equal to in. So you could say the composition function of S of t is in, and t of s is in. You can replace this for that. What is in, you might ask? Well, it goes from Rn to Rn. In, the definition is I of x is equal to x. That's the identity matrix in function notation for all x in Rn. So let's look at an example of this just in R, in algebra. Let's let f go from R1 to R1, where f of x is equal to x cubed. Let's find the inverse. Well, if you remember from our algebra days, to find the inverse, we solve the equation y equals x cubed for x. So let's go ahead and do that. So to solve for x, I'm just going to take the cube root of both sides. And so x is equal to the cube root of y, which, by the way, we can write as y as 1/3. So this right here is our inverse. Our inverse is going to be y to the 1/3. Or we can write it in terms of x as, so it looks like above, f inverse of x is equal to x to the 1/3. So let's check this. So let's look at f actually I'm doing the second one first, aren't I? Which is the same as f of f inverse of x. What is that equal to? Well, if I look at f inverse we found out was x to the 1/3. And I'll plug that back in for f. There it is. That would be x to the 1/3 cubed, which is indeed x. If we did it the other way around, just to check, that would be f inverse of f of x, which is x cubed. And then now we're going to put an x cubed in for the inverse right there. So that would be x cubed to the 1/3, which is still x. So therefore, this is indeed the inverse. What does this look like with matrices, with our transformation, our linear transformation? If you remember our standard linear transformation, all linear transformation, you can find a standard matrix. And let's assume A is invertible. If that's the case, you're going to see that the inverse, and again you can call this t inverse of x, but the inverse is just going to end up being A inverse times x. So they have a picture of it here in figure 2. Here, this is our matrix multiplication, right? This was t, and therefore equaling ax. And then if we go back the other way, it's just going to be, this one is going to be s is equal to A inverse of x. Let's change that to t of x. And of course, these are all vectors. Let's check that. So let's look at t of s of x. See what that is. So we have t of what's s of x? It was a, we claim that it's this. So what is that going to equal to? That's going to equal to, well, I'm going to plug this in for my x of my t, so I have a inverse x, which you could just really redirect this and make this a inverse. And we know, since a was invertible, that that is just x. We can check the other way around. So we know that t is just ax. What's s of ax? I would plug the x in here. So I'd have a inverse of ax. And again, I can just change my parentheses. And again, since a is invertible, that is also x. So you can see the identity is just x with our inverse functions. Which brings us to our next theorem. It says that if t, it goes from Rn to Rn, is a linear transformation, and let A be the standard matrix for that transformation, T is invertible if and only if A is an invertible matrix. So T is invertible if and only if A is invertible. And then in that case, the linear transformation S is going to give in by, just like what we said above, A inverse X. And by the way, it's unique. You can see that it's unique in the book if you look at exercise number 39. The following here is the proof. So this is going to go this way. So we're going to assume that T is invertible. It's an if and only if statement. So we want to show that A is invertible. So we know from 2 that T is onto. So what is 2? You can look up in the book and see that 2 is the statement T of S of x is equal to x for all x in Rn. So because of this, it's onto. It explains it right here. So if you pick a B, so if B is in Rn, pick a B, and let x equal S of B, then T of x is equal to T of S of B, because that's what x is, which, by the way, by this is just B. So for every B that we pick, we found an x, therefore it's onto. And for each B is in the range of T. And therefore, by the invertible matrix theorem, we know that when the transformation T of AX is onto, we know that A is invertible. You can go back and look at that in the last video. Conversely, we're going to go this way. We're going to suppose A is invertible, show T is invertible. So if A is invertible, well, we're going to just do what I did up here. We found it. S of x is equal to A inverse x. And I already did that one up there. And S is a linear transformation, so we know that if you just do this check that I did, you're going to get S of T of x equals x. In fact, I did it both ways. Therefore, T is invertible. Let's look at the following example. Let's find the standard matrix of a 90 degrees clockwise rotation about the origin in R2 using inverses. So if you remember from chapter 1, we had a formula for counterclockwise. So I want to use that formula to see if I can then find the inverse and have it be clockwise. So let's let T go from R2 to R2, be the transformation that rotates each point in R2 about the origin through an angle theta, where with a counterclockwise rotation for a positive angle. We have this formula. If you remember, T of x is equal to AX, where A is cosine of theta, sine of theta in the first column, and then negative sine of theta, cosine of theta. You can find this in example 3 in section 1.9. So what we're going to do is use 90 degrees We're going to, because we want just a 9-degree angle. So if I plug in 90 degrees, I get 0, 1, -1, 0. That should rotate. You can check it. 90 degrees in a counterclockwise direction. We'll check that in a minute. So S of x, which better be, right? We know that is T inverse of x. It's just going to be A inverse times x. So what is A inverse? It's a 2 by 2. So we can say, we can actually just use the formula. So here's the formula. So what is A inverse of x? So first of all, AD minus BC, we know is 0. AD minus a -1, so it's 1. So that doesn't change anything. And so A inverse is just 1 times. And then we're going to switch these, so they're both 0. We're going to make these negative, and that should be the answer. Let's make this a little smaller so we can see it. We found the standard matrix. So let's just check this. So if we take A inverse times our AB, we will get B negative A. So you can check that here. You get a B there and then a negative A. Decided to change this to grid paper so we can see this. So we're looking at the point B negative A. So that means that this height would be the X position. So that would be A1 that way. And then a negative A down, just so we can see that. It does now rotate in a 90 degrees. It does work. And by the way, I did say I would check this if you make this A times the AB. What would that be? We've done this before, but that would be negative B. So that would be negative B would be here, right? Because that's a plus B there. Negative B here, and then A up. That was counterclockwise. Let's try another example. Let's determine whether the projection onto the x1 axis is an invertible transformation. Are all transformations invertible? Let's recall first what a projection onto the x1 axis was. If you remember, this is the standard matrix that did that projection. So there it is, where A is going to be this matrix. So if I look at the inverse, oh, that's going to be, it does not exist. Why? Because if you look at AD minus BC, it's equal to 0. Therefore, T inverse, by our theorem, does not exist. It is not invertible. That theorem right there. T is invertible if and only if A is invertible. Our standard matrix. So let's look at example 2 in the book. Last example. What can you say about a one-to-one linear transformation from Rn to Rn? Well, the answer is it is invertible. Why? Well, we know from the invertible matrix theorem or from theorem 12 and 1.9 that if you have a one-to-one function, then your standard matrix, the columns, are linearly independent. If they're linear independent, again, by the invertible matrix theorem, we know A is invertible. And T maps Rn onto Rn. So T is invertible.